dark matter as unfilled gravitational terrain. Dark matter enters physics as an observational name, not an explanatory one. It labels a mismatch between how matter moves and how much luminous matter we can see without committing to what physically must be present. This section keeps that original humility intact while reframing what the observations are actually measuring. The proposal is not that dark matter does not exist, nor that current models are wrong, but that dark matter phenomena may be recording the shape of gravitational terrain rather than the presence of unseen particulate mass. What is being inferred is structure, not substance. When rotation curves are measured in galaxies, the surprising result is not merely that stars move faster than expected, but that their velocities remain stable across large radii. The usual interpretation is that additional mass must be present to deepen the gravitational potential. That interpretation is consistent and useful, but it is not the only way to read the data. From a geometric perspective, what rotation curves directly reveal is that the curvature governing orbital motion does not fall off in the way naive luminous matter accounting would suggest. The measurement does not detect particles, it detects constraint. Matter traces a potential that is already there, whether or not that potential is visibly occupied. Gravitational lensing reinforces this point even more directly. Lensing maps curvature by observing how light paths bend. Light has no rest mass and no internal structure that could plausibly generate the curvature it follows. It is an almost ideal tracer. When lensing indicates more curvature than luminous matter alone would predict, what is being observed is geometry. The standard interpretation assigns that geometry to unseen mass. But the observation itself does not demand particulate explanation. It demands only that the terrain be shaped in a particular way. The data constrain the map, not the material composition of the map. This distinction becomes clearer with an analogy. Imagine a landscape at night. A map records hills, valleys, and basins, regardless of whether streetlights are installed. A lighting system shows where illumination exists, not where the terrain rises or falls. Luminous matter functions like lighting. It reveals where matter is radiating, interacting, or chemically active. Gravitational measurements function like topographic surveying. They reveal slopes, depths, and pathways. When a map shows a valley that lacks lights, the correct conclusion is not that the valley is unreal, but that it is unlit. In this framing, dark matter corresponds to mapped gravitational terrain without luminous occupation. Importantly, this reinterpretation does not deny that mass contributes to curvature. General relativity, as formulated by Albert Einstein, explicitly couples stress energy to geometry. Matter modifies the terrain it occupies. The claim here is narrower and more careful. Observed curvature need not always be attributed to currently present radiating baryonic matter. Curvature can exist as part of the global gravitational architecture, and matter, moving through it, will respond accordingly, whether or not that curvature is visibly sourced. This perspective also avoids proposing alternatives to particle dark matter, modifying gravity, or falsifying existing cosmological models. No competing particle candidates are introduced. No adjustments to lambda CDM are claimed. No advocacy for MOND or similar frameworks is implied. The goal is interpretive, not adversarial. It asks what the measurements themselves strictly require and what assumptions are added afterward for modeling convenience. By treating dark matter phenomena as measurements of unfilled gravitational terrain, the observational facts remain untouched while the causal story is simplified. Rotation curves indicate persistent curvature. Lensing indicates structured geometry. Matter and light trace what is already shaped. Whether that shape is later explained by particles, fields, or deeper geometric principles is a separate question that does not need to be answered here. This separation is deliberate. Dark matter occupies volatile conceptual ground, and entangling it prematurely with ontological claims risks destabilizing otherwise solid arguments. By isolating it, the framework protects its earlier foundations while offering a reinterpretation that is compatible with observation, respectful of existing theory, and cautious about claims. What dark matter measures most directly may not be what fills space, but how space itself is shaped. Known scientific support for dark matter as measured gravitational terrain. The reinterpretation of dark matter phenomena as measurements of gravitational terrain rather than direct detections of unseen particulate mass is already compatible with how the observations themselves are performed. None of the primary dark matter evidence detects particles. What is measured in every case is motion or deflection. Rotation curves measure orbital velocity as a function of radius. Gravitational lensing measures the bending of light paths. Large-scale dynamical studies measure stability and coherence over time. In all cases, the observable is a response to curvature, not a census of matter. The inference of mass is a secondary modeling step layered on top of geometric data. Rotation curves provide a clear example. What telescopes actually record is how fast luminous matter moves at different distances from a galactic center. The data show that orbital velocities remain high, far beyond where visible mass declines. This directly constrains the shape of the gravitational potential. It does not by itself specify what generates that potential. Assigning the curvature to unseen mass is a reasonable and productive interpretation, but it is not forced by the measurement. The observation demands a persistent gravitational well. It does not demand a specific ontological filling of that well. Matter is again acting as a tracer, sketching the terrain it moves through rather than proving what the terrain is made of. Gravitational lensing strengthens this point because it removes even baryonic matter from the tracing process. Light follows null geodesics determined entirely by spacetime geometry. It has no rest mass and contributes negligibly to curvature. When lensing maps reveal more curvature than luminous matter alone would predict, what is being measured is the shape of spacetime itself. The lensing signal does not differentiate between curvature sourced by particles, fields, or pre-existing geometric structure. It records only that curvature exists and has a particular configuration. Observations by institutions such as the European Southern Observatory consistently demonstrate that lensing is a geometric probe first and a mass inference tool second. This separation between measurement and interpretation is already acknowledged implicitly in mainstream physics. Dark matter is treated as an effective description, not a directly observed substance. The standard lambda CDM framework does not begin with particle detection. It begins with gravitational effects that are then modeled as mass distributions because that approach integrates well with existing theory. Nothing in this reinterpretation denies the utility or success of that framework. It simply points out that the observations constrain curvature more directly than composition. General relativity itself supports this distinction. The theory relates spacetime curvature to stress energy, but it does not require that every instance of curvature be attributed to locally present, luminous baryonic matter. Curvature is a field defined across spacetime. Matter contributes to it, but geometry is not reducible to a list of particles at every point. Once curvature exists, motion and light respond to it, regardless of whether its source is visible. This is a direct consequence of the geometric formulation introduced by Albert Einstein, not an external reinterpretation imposed from outside the theory. The terrain without luminance analogy mirrors how physicists already separate gravitational mapping from electromagnetic observation. Astronomical surveys routinely distinguish between mass distribution inferred from dynamics and luminosity, distribution inferred from radiation. These are known to diverge. Treating that divergence as evidence of unlit terrain rather than immediately as proof of unseen particulate occupants does not contradict any measurement. It reframes what the data are strictly telling us versus what is added for explanatory closure. Crucially, this support does not rely on rejecting particle dark matter, modifying gravity, or dismantling cosmology. It does not claim falsification of lambda CDM, propose alternatives to it, or advocate Mond-like frameworks. It remains agnostic about the ultimate explanation while sharpening the interpretation of what is already observed. Dark matter phenomena, as currently measured, are measurements of gravitational structure. Whether that structure is filled, partially filled, or unfilled by matter is a subsequent question, not one answered directly by the data. By keeping this distinction explicit, the framework aligns closely with existing scientific practice while clarifying a common conceptual shortcut. Observations map curvature, models populated. Recognizing that difference allows dark matter to be discussed as gravitational terrain without destabilizing the rest of the theory or overstepping what the evidence itself can claim.